I've lost count of how many times I've seen a kid rip open a robot kit, stare at the pile of parts inside, and freeze. The excitement's there, sure, but so is the panic. They want to build something cool. They just have no idea where to begin. My name is Kazuki Tanaka, and I've spent the last 8 years testing robotics platforms, equipping makerspaces, and rebuilding failed projects with frustrated kids at all hours of the night. Here's what I've learned. The best first robot isn't the one packed with the most features. It's the one a kid can finish in under an hour and start tinkering with immediately after.
You're listening to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, the research, the data, the testing, the script, all of it is written and verified by real people. But the voice you're hearing right now is AI generated. We're upfront about that because transparency matters. Now, if you've been listening for a while, thank you. Seriously, it's listeners like you who make this show possible. And if you're new here, welcome aboard. This is where we break down STEM learning tools, robotics kits, and hands-on projects in a way that's actually useful. We drop new episodes every Monday, Wednesday, and Friday, so you've got a steady stream of content coming your way. All right, let's jump into today's episode on building your first robot with a kit. So let's cut straight to it. How do you actually build your first robot with a kit? It comes down to 3 things: choosing hardware with crystal clear visual instructions, immediate feedback mechanisms like LEDs and motors that actually move when they're supposed to, and a programming interface that matches your child's current skill level, not just their age. I've celebrated with an 8th grader who finally debugged her first autonomous navigation routine, and I've also been there at 11 at night trying to salvage a project that went sideways. The difference between a kit that builds real skills and one that ends up collecting dust in a closet? Lab-tested compatibility, honest difficulty ratings, and a clear path forward to the next challenge. Now, let's talk about what you should actually look for when you're ready to build that first robot. The first time you build a robot pretty much determines whether you'll ever build a second one. That's why I always look for visual assembly guides that use actual photographs or high-contrast diagrams, not cartoon approximations that skip over critical details like which way a part is supposed to face. Physical compatibility matters more than most people think. After testing over 40 kits in our fabrication lab, I've learned that snap-fit connections work better than screws for kids under 10, while threaded fasteners teach valuable mechanical concepts for kids 11 and up. Here's the thing about immediate mechanical feedback. It separates great kits from frustrating ones. When a motor mounts correctly, it should sit flush and spin freely. When a sensor clicks into place, you should feel it lock. The LEGO Education Spike Prime system does this brilliantly. Every connection produces tactile and audible confirmation. I've watched kids self-correct assembly errors simply because the parts didn't feel right when they were misaligned. Progressive complexity matters too. Your first build should have somewhere between 15 and 30 parts maximum. Anything beyond that introduces decision fatigue before kids get to experience success. I typically recommend starting with a 2-motor wheeled platform. It teaches drivetrain basics, weight distribution, and gear ratios without overwhelming new builders. Moving on to programming interfaces, this is where most families stumble. They pick a robot based on features, not on programming readiness. Block-based interfaces like Scratch or Blockly work well for ages 7 to 12 and for visual learners. Text-based languages like Python or C++ suit kids 12 and up, or kids who are transitioning from block coding. But compatibility goes deeper than just age ranges. I test every kit against these technical requirements. Operating system support, whether it works on Windows, Mac OS, Chrome OS, iOS, or Android. Offline capability, does it require a constant cloud connection? And IDE familiarity, does it use industry-standard tools? The Vex IQ platform supports Vex code blocks and Python in the same environment. Kids can switch languages without changing hardware. That's a proper learning path, not a dead end. Connection method matters for household compatibility too. Bluetooth LE works on most modern devices, but drains batteries. USB-C provides power and programming but tethers your robot to a cable. Wi-Fi enables advanced projects but requires network configuration. I've seen too many families buy robots that won't connect to their 3-year-old iPad or Chromebook. Check the compatibility matrix before you buy, not after. Let's get into the lab specs. Power architecture determines whether your robot becomes a long-term platform or a one-off project. Rechargeable lithium batteries like 18650s or LiPos cost more upfront but eliminate the AA battery drain that kills enthusiasm. I calculate cost per build hour in my lab testing. Disposable batteries run about 50 to 75 cents per hour. Rechargeable systems drop to 5 to 10 cents after the initial investment. Safety matters with power systems. Look for built-in battery management, things like overcharge protection and thermal monitoring, and keyed connectors that prevent reverse polarity. The best educational kits use USB-C charging. It's the emerging standard, and families already own compatible chargers. I've retired every micro USB robot in our teaching inventory. That connector standard is dying, and you shouldn't build skills on deprecated technology. Expandability determines longevity. Can you add sensors later? Does it accept third-party components, or are you locked into proprietary parts? I measure this by counting available GPIO pins, communication protocols like I2C, SPI, and UART, and voltage compatibility, whether it's 3.3 volts or 5-volt logic. A robot with 4 expansion ports and I2C support can evolve into an autonomous vehicle, an environmental monitor, or even an art installation. A closed system hits a capability ceiling in about 6 months. Now let's talk durability, because this matters more than you think. I drop robots. I drive them into walls. I leave them in hot cars. This isn't sadism, it's testing whether a kit survives actual childhood. ABS plastic components handle impact better than 3D printed PLA parts. Metal gear motors outlast plastic gears under load. Modular electronics, like replaceable sensor boards, cost more than all-in-one circuit boards, but they let you repair rather than replace.
Pay attention to connection durability. Friction-fit wire headers loosen after 20 to 30 insertions. JST connectors handle hundreds of cycles. I've rebuilt the same beginner robot 15 times with different student groups. The kits that survive this abuse use strain relief on wiring, fretted inserts in structural parts, and keyed connectors that can't be forced backward. Repeated disassembly teaches mechanical design, but only if parts don't strip or crack. I count rebuild cycles in my lab notes. Quality kits survive 50 or more builds before showing wear. Budget kits start failing around build 10. That's not a value judgment. Sometimes a 10-build lifespan matches your learning goals perfectly. Just know what you're buying. Here's something that catches families off guard: subscription requirements and hidden costs. Some robotics kits operate forever with 0 recurring costs. Others require monthly software subscriptions, curriculum licenses, or consumable part replacements. I maintain a spreadsheet tracking total cost of ownership over 3 years. The pattern holds. Budget kits with $8 to $15 per month software fees often cost more than premium kits with lifetime licenses. Curriculum access varies wildly. Some companies include comprehensive lesson plans, video tutorials, and challenge libraries with purchase. Others charge $40 to $120 annually for educational content. I'll be direct. Kids rarely follow packaged curriculum beyond the first 3 lessons. They want to build their own ideas. Paid curriculum makes sense for classroom settings or structured homeschool programs. For casual skill building, skip it. Consumables kill budgets silently. Does the kit use specialty batteries, proprietary sensors, unique fasteners? I've seen families spend $200 on a robot, then discover that replacement motors cost $35 each and wheel encoders run $45. The manufacturer's parts catalog tells you everything. Read it before buying. All right, let's get into our top picks for building your first robot. First up is the LEGO Education Spike Essential Set for ages 6 to 8. Check the link below to see the current price.
This kit bridges construction toy familiarity with programmable robotics through 449 LEGO Technic elements, a medium intelligent hub with 2 motors and 2 sensors, and scratch-based drag-and-drop coding. I've used this in 3 different Maker Lab programs. Kids who already play with LEGO immediately understand the assembly language. They spend mental energy on programming and engineering, not decoding instructions. Universal compatibility with existing LEGO collections means kids can integrate bricks they already own. Offline programming support means no internet required after the initial app download, and it works on Windows 10 and up, Mac OS, iOS, Android, and Chrome OS. There's a built-in lesson library included with purchase, no subscription required for over 50 structured projects. The hub has a rechargeable battery that eliminates the AA battery replacement cycle. And the damage-resistant ABS construction is tough. I've had these survive drops from 4-foot tables onto concrete repeatedly. What doesn't work as well? Limited sensor variety compared to advanced platforms. You get 2 small motors, 1 color sensor, and 1 distance sensor, which restricts project complexity. It's a closed ecosystem. You cannot integrate non-LEGO electronics without third-party adapters. The processing power has a ceiling. It struggles with complex multi-threading or rapid sensor polling. And the small motor torque is insufficient for robots exceeding 500 grams total weight. From a lab spec standpoint, the hub draws 12 volts from a rechargeable lithium battery with micro USB charging and a 2 to 3 hour runtime. Bluetooth 4.2 connectivity with about 10 meters of range. Storage case is included. Expansion requires LEGO education sensor packs that run $30 to $90 each. Next is the MakeBlock MBot 2 for ages 8 to 12. Check the link below to see the current price. This delivers a CyberPi controller with Wi-Fi and AI capabilities, aluminum chassis construction, and tri-mode programming using MBlock blocks, Python, or API in a wheeled robot platform. I've logged over 200 build hours with this platform across summer camps and after-school programs. It's the kit I recommend when families ask me what teaches real programming but doesn't overwhelm a 4th grader. What works? A true progression path where the same hardware supports block coding at age 8, Python at age 12, and API development at age 15. Wi-Fi and Bluetooth dual connectivity enables IoT projects and remote control without dongles. The aluminum frame withstands crashes. I've had one survive a full school year with 25 different students. It's an open ecosystem that accepts Arduino shields, Grove sensors, and third-party components via expansion ports. And the built-in sensors include ultrasonic, line following, light, and sound sensors in the base kit. What doesn't? MBlock app stability issues on Chrome OS. It works better on Windows, Mac OS, or iPad. Small wheels slip on carpet. It works best on hard floors or requires aftermarket tire upgrades. The battery compartment door is fragile. The securing clip breaks after 40 to 50 battery changes. And the documentation assumes basic electronics knowledge. It struggles to explain GPIO concepts to complete beginners. Powered by 3 18650 lithium rechargeable batteries with USB-C charging and a 5 to 6 hour runtime. The CyberPi runs at 240 MHz with 2 MB of RAM. 8 GPIO ports support I2C, UART, and SPI. Metal gearbox motors are rated for 1 kilogram load capacity. The expansion ecosystem includes over 60 compatible sensors and actuators. Moving on to the VEX IQ Kit 2nd generation for ages 8 to 14. Check the link below to see the current price. This provides competition-grade plastic components, snap-together construction requiring 0 tools, and VEX code software supporting blocks or Python. This is the platform used in over 18,000 schools globally, and in official VEX IQ robotics competitions. I maintain 2 sets in my fabrication lab, one for teaching, one permanently disassembled for parts inventory research. What works? A competition pathway that directly prepares students for VEX IQ challenge events and team robotics. Extensive parts ecosystem with hundreds of structural, motion, and sensor components available individually. touch sensors and smart motors, where the motors include built-in encoders for precise movement control. Robust mechanical connections, where plastic pins lock positively and survive over 100 assembly cycles. And the controller supports 12 smart devices, so it scales from simple robots to complex multi-mechanism machines. What doesn't? Proprietary ecosystem means you cannot use Arduino sensors or standard hobby electronics without adapters. Higher entry cost, where the base kit includes fewer sensors than comparably priced competitors. Large physical footprint means storage requires more space than compact kits. And the brain unit uses non-standard USB, requires a VEX-specific cable that's easy to lose and annoying to replace. Lab specs: the brain runs an ARM Cortex M4 processor with 12 smart ports. Rechargeable 1100 mAh battery with a custom charger included, 3-hour charge time and over 90 minutes of runtime. Compatible with Windows, Mac OS, Chrome OS, iOS, and Android. Aluminum chassis extensions are available for advanced builds. Meets ASTM F963 toy safety standards. Next up is the Elegoo Smart Robot Car Kit version 4.0 for ages 12 and up. Check the link below to see the current price. This ships as an Arduino Uno R3 compatible platform with over 24 modules, including ultrasonic sensors, line tracking, infrared remote, Bluetooth app control, and a camera module. This isn't a kid's toy, it's a legitimate robotics development platform that teaches industry-standard tools. I use these in my teen fabrication workshops because they bridge educational kits and professional prototyping.
What works? Arduino IDE compatibility means it uses the actual software employed by professional embedded engineers. Comprehensive component library includes sensors and modules that support over 15 different project types. Extensive documentation with PDF tutorials, sample code, and video guides covering every included component. Open source platform integrates with millions of existing Arduino libraries and community projects. And it's camera and computer vision ready. The OpenCV-compatible camera enables AI and image processing projects. What doesn't? Requires soldering for some expansions. Not all sensors use plug-and-play connectors. C++ programming only, no block-based interface, assumes text-based coding experience. Assembly instructions assume technical literacy. Terms like GPIO, PWM, and I2C appear without basic definitions. Fragile camera mount where the plastic bracket cracks if the robot tips over during testing. And no offline app control. Bluetooth requires an Android device with constant connection. Lab specs: Arduino Uno R3 clone with ATmega 328P microcontroller, 16 MHz, 32 KB flash, and 2 KB SRAM. Powered by 18650 batteries with dual slots, 2 to 3 hour runtime, and USB charging. Sensors include HC-SR04 ultrasonic with 2 to 400 cm range, TCRT 5000 line tracking with a 5-channel array, IR receiver, and servo motor drivers. Compatible with 5-volt logic sensors. Expansion requires basic breadboarding and jumper wire skills. Now, let's look at the Wonder Workshop Dash robot for ages 6 to 11. Check the link below to see the current price. This arrives fully assembled with no construction required. Kids program immediately using Wonder, Blockly, or Swift Playgrounds apps. This is the robot I recommend for families who want programming results within 15 minutes of opening the box. I keep one in my workshop for testing age-appropriate interface design. Its approachability is unmatched. What works? Zero assembly required eliminates the mechanical skill barrier for pure coding focus. Multiple app progression where Wonder for ages 6 and up, Blockly for ages 8 and up, and Swift Playgrounds for ages 10 and up all use the same hardware. Voice recording and playback where personality features engage younger learners effectively. Robust construction survives drops, collisions, and general rough handling from elementary age users. And it's wireless charging compatible with no cables to manage if you buy the optional charging dock. Closed hardware means you cannot modify, repair, or expand the physical robot in any way.
Limited mechanical learning. It teaches programming but zero assembly, gearing, or engineering concepts. iOS is heavily favored where Android and Windows apps lag behind in features and stability. Expensive for a single-function device, it does only programming unlike construction-based kits. And proprietary accessories like the launcher, bulldozer, and gripper attachments cost $20 to $50 each. Lab specs: internal rechargeable battery with micro USB charging and 5-hour runtime. Bluetooth LE connectivity for iOS 11 and up, Android 5.0 and up, Fire OS 5.0 and up, with limited Windows support. Built-in sensors include 12 proximity sensors, a 3-axis accelerometer, gyroscope, and wheel encoders. You cannot add external sensors or modify electronics. Dimensions are 16.5 by 17 by 19.5 centimeters, weighing 870 grams. Last one is the Littlebits Droid Inventor Kit for ages 8 to 14. Check the link below to see the current price. This combines magnetic electronic modules with Star Wars R2-D2 design, app-guided missions, and block-based coding through the Littlebits Invent app. I tested this extensively in 2023 and 2024 with mixed age groups. The magnetic connections remove electronics intimidation. Kids experiment fearlessly because nothing can be wired incorrectly. What works? Magnetic connections prevent wiring errors, polarity-enforced modules only connect in correct configurations. Themed engagement, where the Star Wars IP motivates reluctant builders. Modular expansion, it's compatible with the entire Littlebits ecosystem with over 70 modules available. Sound and light effects, where personality features enhance emotional connection to the project. And no soldering, no breadboards, pure snap-together electronics. What doesn't? Proprietary magnetic system means you cannot integrate standard electronics components or Arduino shields. App dependency requires a tablet or phone for programming, no desktop software or offline capability. Limited programming depth, where blocks focus on sequencing, less robust than Scratch-equivalent platforms. And modules are expensive to replace. Individual components cost $8 to $35 each. And this is a discontinued product line. Sphero acquired Littlebits in 2019, so future support is uncertain. Now let's tackle some frequently asked questions.
What age should a child start building robots with kits? A child can start building robots as early as age 6 with snap-fit construction systems like Lego Spike Essential or pre-assembled programmable robots like Dash, but the optimal starting age depends on skill outcomes rather than chronological age. I've taught robot building to 5-year-olds who could follow visual assembly instructions and manage block-based programming, and I've worked with 12-year-olds who needed to start with screen-free coding fundamentals before tackling robot construction. The key indicators are fine motor skills sufficient to connect components without frustration, pattern recognition to follow assembly sequences, and persistence to debug when code doesn't produce expected behavior. Kids who can complete 50-piece Lego sets independently and play basic logic puzzle games are typically ready for entry-level robotics kits. Those who struggle with multi-step instructions benefit more from screen-free coding toys that build sequencing skills before introducing robot construction. Do robotics kits require programming knowledge before starting? No, modern robotics kits designed for beginners include 0 prerequisite programming interfaces that teach coding concepts through guided missions and visual block languages, but the learning curve varies significantly between platforms. I've watched complete programming novices succeed with kits using Scratch-based or Blockly interfaces. These platforms use drag-and-drop command blocks that eliminate syntax errors and let kids focus on logic rather than typing accuracy. The LEGO Education Spike Essential and Vex FIQ kits include tutorial sequences that teach programming concepts like loops, conditionals, and variables through robot challenges. Kids learn by doing rather than studying theory first. However, kits built around Arduino or Raspberry Pi platforms assume basic programming literacy and work better as second or third robots after kids master block-based coding. For families with 0 programming experience, I recommend starting with platforms that offer example programs you can load immediately. Seeing the robot move builds confidence before kids modify code. The progression typically takes 15 to 30 hours of hands-on time to move from load pre-written code to write original programs, and this timeline holds consistent across ages 8 to 14 in my workshop experience.
What's the difference between toy robots and educational robotics kits? Educational robotics kits emphasize modifiable construction, programmable behavior, and expandable capabilities that build transferable engineering skills, while toy robots prioritize entertainment through pre-programmed behaviors and fixed designs that offer minimal learning progression. I draw this distinction in my fabrication lab constantly. A $60 toy robot might walk, talk, and respond to voice commands impressively, but if kids can't modify its programming, disassemble its mechanics, or expand its capabilities, it teaches observation rather than creation. Educational kits, even simple ones like MBOT 2 or Spike Essential, let kids change the code, rebuild the structure, add new sensors, and create original projects. The skill-building difference becomes obvious after 3 months of use. Toy robots get played with less frequently as novelty fades. Educational kits evolve into weather stations, obstacle-avoiding vehicles, or interactive art installations because kids can transform them into whatever their imagination demands. From a technical standpoint, educational platforms use open or documented programming interfaces like Scratch, Python, or Arduino IDE that connect to industry-standard tools, while toy robots use proprietary apps with limited functionality. The price difference reflects this capability gap. Educational kits cost more because they're platforms for dozens of projects rather than single-purpose devices.
How long does it take to build a first robot from a kit? Assembly time ranges from 30 minutes for snap-fit platforms to 3 to 4 hours for screw-based construction kits. But achieving a functional programmed robot requires an additional 1 to 2 hours of coding and testing regardless of assembly complexity. I track build times in my workshop logs across different age groups and skill levels. 6 to 8-year-olds need 45 to 90 minutes to assemble a Lego Spike Essential robot following instructions, then another 60 to 90 minutes to complete basic programming challenges. 10 to 12-year-olds cut assembly time to 30 to 60 minutes but spend similar duration on programming because they attempt more complex behaviors. Arduino-based kits, like the Lego Smart Car, require 2 to 3 hours of careful assembly following wiring diagrams, managing cable routing, and mounting sensors correctly, plus another 2 to 4 hours of programming setup, library installation, and code troubleshooting. These timeframes assume uninterrupted work sessions. Real-world builds typically span 2 to 3 days, as kids work in 45 to 60-minute sessions. The critical metric isn't speed, it's achieving independent movement within the first session. Kits that deliver visible results quickly, motors spinning, LEDs blinking, wheels turning, maintain engagement. Those requiring extensive assembly before anything happens risk frustration. I recommend planning first builds across 2 separate days. Day 1 for construction and basic connectivity testing, Day 2 for programming experiments and modifications. This pacing prevents mental fatigue and gives kids time to think about what they want their robot to do next.
Can siblings with different ages use the same robotics kit? Yes, platforms with multi-level programming interfaces and rebuildable construction specifically suit age-spanning collaboration, with certain kits supporting 6 or more year age gaps through progressive challenge paths. I've successfully deployed shared robotics kits in families with children aged 7 and 13, 9 and 15, even 6 and 12. The configuration that works, kits like MakeBlock MBOT 2 or Vex IQ, where younger siblings handle construction and simple block-based programming while older siblings tackle advanced features like sensor fusion, autonomous navigation, or text-based Python coding. The hardware serves both skill levels simultaneously. Younger kids build confidence through achievable challenges, while older kids push capabilities through complex projects. The approach fails when kits lock into single difficulty levels. A kit perfect for an 8-year-old bores a 14-year-old within weeks, while a kit designed for teenagers frustrates elementary-age children. I specifically look for documented progression paths that span 3 or more years of skill development.
Lego Spike Essential serves ages 6 to 10, then transitions to Spike Prime for ages 10 to 14, maintaining construction familiarity while advancing capabilities. The Vex IQ platform scales from simple block-coded robots at age 8 to competition-grade autonomous machines at age 14 using identical hardware. For families investing in shared equipment, prioritize open-ended platforms with extensive expansion ecosystems over age-specific kits with capability ceilings. Siblings can collaborate on construction while pursuing separate programming challenges suited to their individual skill levels. So, here's the verdict. Building your first robot with a kit should feel like unlocking a capability, not solving a puzzle. I've rebuilt enough failed first attempts to know exactly where families stumble. Unclear instructions, programming interfaces that don't match actual skill level, or robots that can't evolve beyond the initial build. Choose based on programming readiness first, features second. A fully assembled robot like Dash gets 6-year-olds coding within minutes. Lego Spike Essential bridges construction familiarity and programming for ages 7 to 10. Vex IQ prepares kids for competition robotics and multi-year progression. MakeBlock MBot 2 offers the smoothest path from blocks to Python. Elegoo Smart Car teaches genuine Arduino development for teens ready to build professional skills. The best first robot is the one your kid rebuilds into something you didn't expect. That's when you know the kit worked.
That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. Just a reminder, we release new episodes every Monday, Wednesday, and Friday, so you're never waiting long for the next one. If you found this episode helpful, I'd really appreciate it if you could leave us a 5-star rating and write a quick review. It makes a bigger difference than you'd think. It's how people who are searching for STEM resources or robotics advice actually find the show. And if you haven't already, hit subscribe or follow so you get notified the second a new episode drops. Thanks again, and I'll catch you in the next one.